Good day, everyone. We are the Group 6. So, this will be our performance innovative task entitled Thermal Expansion and Contraction of Tiles in Outdoor Areas. So, before anything else, let us first meet the group. I am Michael Andre B. Kitariano together with
Zenon Perez.
Joshua Byron.
Hans Platan.
and Zan Kanuran Yeses.
and we are the Group 6. Next slide, please. So, this is the overview of the problem. So, the situation involves the expansion and contraction of ceramic tiles, typically found in outdoor environments like mall corridors or verandas. Especially during hot days and cooler nights. When tiles are heated by direct sunlight, they expand, and as temperatures drop in the evening, they contract. This repeated process leads to ceramic tiles coming loose from their base if not properly managed during design and installation. So to precisely forecast how the temperature of these tiles varies over time, a mathematical model was employed, which is based on Newton's law of cooling. This law explains that the speed at which an object cools down is directly related to the difference in temperature between the object and its environment. So grasping this cooling mechanism is important for civil engineers to prevent possible harm and enhance the durability of tiled surfaces in outdoor areas. Next slide, please.
So for our modeling approach, the temperature of a set ceramic tiles in the outer corridor of a mall is at 32 degrees Celsius. During the day, the tiles are exposed to direct sunlight, raising its temperature to 40 degrees Celsius. As the sun sets, the tiles begin to cool down. Assuming the cooling process follows Newton's law of cooling with a cooling constant of K is equals to 0.02 per minute. So in this scenario, we assume that the initial temperature of the tiles after exposure to sunlight is 40 degrees. The ambient nighttime temperature when the tiles begin to cool was 32 degrees, and the cooling constant of K is equals to 0.02 per minute was selected, which approximates how ceramic tiles interact thermally with the environment. Resolving up for practical solution. Using these conditions, Newton's law of cooling was expressed as a first-order differential equation. Step 1, rewrite the differential equation, which is dt over dt is equals to k times t minus t sub m. Then we separate variables by isolating the terms involving t on the left side and the differential dt on the right side. So we integrate both sides and then we'll end up with the new equation ln times t minus tm equals to k plus c. Then as we go further, the new equation will be t is equals to tm plus c1 e raised to k times t. So for our assumptions, t is equals to 40 degrees Celsius, t sub m is equals to 32 degrees Celsius, and our time, which is t, is equals to 0. And in step 4, solve for the arbitrary constant c by using the initial condition t is equals to 40 degrees Celsius. So the equation we use will be t is equals to t sub m plus c1 e raised to k times t. So we substitute their values with their corresponding variables. So 40 is equals to 32 plus c1 e raised to k times t. So our t is equals to 0. Then 40 minus 32 is equals to c1 e raised to k times 0, and our arbitrary constant or c1 is equals to 8 degrees Celsius. Then step 5, express the solution in terms of t of t by exponentiating both sides and determining the constant from the initial condition. So our new temperature will be 35 degrees. So same equation, we will use t is equals to t sub m plus c1 e raised to k times t, where rt is unknown. So substitute the values of their corresponding variables. So 35 as our temperature is equals to 32 as our ambient temperature plus E as our constant, and E raised to K, which is 0.02 per minute, times T. So we subtract 35 and 32, so it equals to 3. Then we divide both sides by 8. So our new equation will be ln times 3 over 8 is equals to 0.02 t. Then ln 3 over 8 is equals to negative 0.981 is equals to 0.02 t. And we divide both sides by 0.02, and our time will be equivalent to 49.05 minutes.
Now, the graph illustrates the cooling of ceramic tiles over time based on Newton's law of cooling. The x-axis represents the time in minutes, while the y-axis shows the temperature of the tiles in degrees Celsius. The graph begins with the tiles at a high temperature of 40 degrees after being exposed to sunlight during the day. As time progresses, the temperature decreases gradually as the tiles cool down, approaching the ambient temperature of 32 degrees Celsius. The graph shows an exponential decrease in temperature, starting at around 40 degrees Celsius and reaching 35 degrees Celsius at approximately 49 minutes based on our solving in the previous reporter. This curve reflects how the rate of cooling is faster initially and slows down as the tile temperature approaches the surrounding air temperature.
For question and answer, for number one, what thermal scenario did you choose and why is it relevant to civil engineer? The article discusses the issue of tile expanding and contracting in outdoor areas such as corridors and verandas, shopping centers, and commercial buildings. These tiles are exposed to sunlight during the day of the cool at night, causing stress and expansion. This is common, can lead to a tile crack and affecting the appearance and safety and the durability of flooring. Poor design or material choice can also cause water rise and exposure, compromising the structure stability and durability of the flooring. For number two, explain the initial assumption you made. The tile initial temperature after a hot day is 40 degrees Celsius, typical or tropical regions. The ambient temperature in the shaded corridor is 32 degrees Celsius after the sunset. The cooling constant is assumed based on the ceramic tile properties and environmental exposure. Based on the real life scenarios, average daily temperatures in Cagayan de Oro.
So number three is, what method did we use to solve the differential equation? To answer this question, we use separation of variables. This method involves rearranging the equation so that all terms involving the dependent variables are on one side and all terms involving the independent variables are on the other side. So this method is useful for solving first order linear derivative differential equations where the rate of change is proportional to the difference between the current state and some equilibrium state. So fourth is, how might the cooling process affect the structural integrity of the material in your scenario? So repeated heating and cooling cycles can cause the tiles to expand and contract, leading to crack or even separation from the base over time, especially with climate change. This constant temperature change can weaken the materials holding the tiles together like glue or grout and cause problems, affecting both the safety and look of the outdoor area. This might make it seem like the chosen material isn't strong or durable enough to handle these conditions, so potentially affecting its overall strength.
So for the last question, what do you think are some additional factors that could influence the cooling rate, and how could this be incorporated into your model? So in our case, we have three additional factors. First is the material properties. Different types of tiles like ceramic, porcelain, and stone have different abilities to conduct heat and expand when heated. These differences affect how quickly they cool down. We can account for this by changing the cooling constant K for each type of material. Next, we have the tile thickness. Thicker tiles might hold onto heat for longer and cool down more slowly. We can simulate this by adjusting the cooling constant according to the thickness of the tiles. And lastly, we have humidity and moisture. Outer tiles that get wet from rain or high humidity might cool down differently because of evaporation. These can change how fast the temperature drops, so we need to consider this when modeling the cooling process. So once again, we are the group 6 and this sums up our performance innovative task entitled Thermal Expansion and Contraction of Tiles in Outer Areas. Thank you.